YOLO is state-of-the-art object detection algorithm, and it is so fast that it has become almost a standard way of detecting objects in the field of computer vision. Previously, people were using sliding window object detection, then more faster versions were invented such as RCNN, fast RCNN, and faster RCNN. But in 2015, YOLO was invented, which outperformed all the previous object detection algorithms. And that's what we are going to discuss today. We will go over the theory on how exactly YOLO works. And in the future video, we will also do coding. So this video is just about the theory behind how YOLO works, and we'll try to see why it is faster. Full form of YOLO is you only look once. Let's say you're working on an image classification problem where you want to decide if the image is of a dog or a person. In this case, the output of neural network is pretty simple. You'll say dog is equal to 1, person is equal to 0. But when you talk about object localization, you're not only telling which class this is, you're also telling the bounding box or the position of an object within the image. So here, in addition to dog is equal to 1 and person is equal to 0, you're also telling about the bounding box. Now, how exactly you do that? So in terms of neural network output, you can have a vector like this where PC is the probability of a class. So here, if there is a dog or a person, then this number will be 1. If there is no dog or no person, this number will be 0. Then the bounding box, so bx, bi, by is the coordinate of the center, which is indicated in yellow circle here. And 60 and 70 is the width and height of this red box. C1 is class 1, that is for dog, so here it will be 1. C2 is for person, and it will be 0. If you have a different image like this, there is a person here. This is my picture in my high school. The PC probability of any class is 1 because there is some object, and these are like bounding box coordinates. And C1 is 0 because it's not a dog, and C2 is 1 because it's a person. And when you have no object in the image, the PC will be 0 and rest of the values don't matter. So now you can train a neural network to classify the object as well as the bounding box. So you can have, I am just showing 3 images here, but you can have, let's say, 10,000 such images. And for each of these images, since it's a supervised learning problem, you need to give the bounding boxes. And the way you give bounding boxes to neural network, understand neural network only understands numbers. So you have to convert this into this kind of vectors. So you will have a vector of size 7 for each corresponding image. So image is x train and y train will be a vector of size 7. You can have 10,000 such images. You can train a neural network in a way that if you input a new image now, it will tell you that particular vector. And now this vector is telling you that this is a dog because C1 is set to 1, and it is also telling you the bounding box. So basically it's essentially giving you the answer for your object detection or object localization rather. This only works for a single object. If you have a multiple objects, what do? Here there is person and a dog in the same image. One might say that, okay, in my image, there could be n number of objects. There could be 2 dogs, 3 people, there could be 5 dogs, 1 person. You don't know how many objects are there in the picture. So it's hard to determine the dimension of your neural network output. If you have one object, it's pretty fixed, right? But if you have n number of objects and you don't know, then determining the size of the output of neural network is hard. You can say upper max is 10. Let's say there will be only 10 objects, and you can have 10 into 7, which is like a 70 size vector. But what if there are 11 objects? See, so that doesn't work. So you have to do something else. All right, so let's say you have this image and there are two bounding boxes that this image has. What YOLO algorithm will do is it will divide this image into this kind of grid cells. So I'm using 4 by 4 grid here. It could be 3 by 3, it could be 19 by 19. There is no fixed rule that it has to be 4 by 4. And for each of the grid cells, for example, this grid cell, you can encode or you can come up with that vector that we saw previously, which is PC bounding box C1 and C2. There are no objects here, so probability of class will be 0, and then rest of the values don't matter. But for this particular grid cell, so I have highlighted here, the dog is there in the picture. See, when dog is expanding to multiple grid cell, you try to find the central place of that dog, and the dog belongs to that particular grid cell. So I'm in this particular cell here, and when I look at the coordinates, you can think about this point as a 0 0 and this point as a 1 1 coordinate. And now you can create this vector where PC is 1, which means you have some object. Then C1 and C2. C1 is for dog, so it is 1. C2 is for person, it is 0. There is person's head here, but the person's center is here. So this person object belongs to this cell. And then 0.05, like this particular distance is 0.05. This is 0.3, because see, this whole thing is 1. And then your bounding rectangle can go out of your grid cell. It is fine. That's why these values are more than 1. So 1.3 and 1. Or sorry, 2 and 1.3. So that is the width. So 2 is this width and 1.3 is height. So it is this height. And now talking about this particular grid cell. So there is a person center here. So we can say person is in this grid, and therefore C2 class value 1 is 1. C1 is 0 because there is no dog. And these are like bounding boxes. So 0.32 is, see, 0.32 is this much. 0.02 is this particular height, and it is 3 because the rectangle width, this yellow line, is equal to almost 3, the size of, see, the width of this grid cell. And if you compare this is 3 times this. That's why I have 3 here. And now you can have for remaining all the cells, the vector will be this. So PC will be 0, remaining will be don't care. So now you have 4 by 4 by 7 volume. Why? Because you have 4 by 4 total grid cells, 16 cells. Each cell is a vector of size 7. That's why I'm saying 4 by 4 by 7. So if you're talking about this top left cell, and if you expand it in a z direction, that will be this vector of size 7. So I hope you're getting an idea. If you don't, please pause the video and just think about what I just said. So now you have the image and then the bounding rectangles. Now you can form your training data set. So your training data set will have so many such images. Let's say I'm showing only 3, for example, but you'll have 10,000 such images. Each image will have bounding rectangle, and based on that rectangle, you will try to derive, you'll first form this kind of grid, 4 by 4 grid, or 3 by 3 or 19 by 19. It varies. It doesn't have to be 4 by 4. And you will come up with the y or a target vector, which will be, for each cell there will be one vector. So there will be 16 such vector per training sample or per training image. Using this, now you can train your neural network, and after you have trained it, it can do prediction. So when you now give this type of image, it can produce 16 such vectors. And why 16? Because this is like 4 by 4 grid, which will basically tell you the bounding rectangle for each of these objects. So this is the YOLO algorithm. It is called you only look once because we are not repeating it. See, we are not doing something like, okay, we have 16 cells. So it's not like we are inputting it 16 times and doing 16 iteration. In one forward pass, you can make all your prediction. That is why it is called you only look once. Now, this is a basic algorithm. We need some tweaks because there could be few issues with this approach. First issue is the algorithm might detect multiple bounding rectangles for a given object. It is possible. So how do you tackle that? So let's think about this. Let's say for a person, it detected all this two yellow and this one white rectangle, and we know by visual observation that this white one is the most accurate one, and the algorithm will also throw out the probability. It will say this is 0.9%. You know, the PC class, it will say this is 0.9% matching with person, and the other rectangles have less probability. So maybe we can look at all the probabilities for a person class and take the max, right? Well, we cannot do this. Okay, if you just take a max, and if there is another person, what happens to that? You don't know where that person is, right? So as a neural network, as a computer, you don't know. So you can't take a max. You have to use different approach. So we use this concept of IOU. So IOU is basically intersection over union, which is you take this rectangle, which is 0.9, this is that white rectangle, and then for that same class, which is person, you will take all other rectangles and try to find overlapping area. And to find overlapping area, you use IOU. So here in this case, see, this is that yellow box, okay? So this is that yellow box here, and this is the white box. And the area indicated in this orange color is intersection area. Area indicated in purple colors is union area. So you find division of these two, and if the objects are overlapping, this value will be more. So let's say if it is the value is more than 0.6 or 0.7, we can say these rectangles are overlapping. If they are completely overlapping, the value will be 1. If they are not overlapping at all, value will be 0. So now we find that these two yellow boxes are overlapping because their IOU is, let's say, greater than 0.65. And then you discard those rectangles. So I discarded all the rectangles which had IOU greater than 0.65 and kept the rectangle which has class probability as max. Okay. So I do this for a person object, then I do the same thing for a dog object. So for dog, I find that, okay, 0.81, this is the max probability. I find all other rectangles in this image. Again, there could be two more dogs here, and there will be rectangles for those also. So you will try to find overlap. Okay, so let's say if there is a dog here, you will not find overlap. So you will not discard that particular rectangle. But this rectangle, you find it to be overlapping, and since 0.81 is max, 0.7 is less, you discard this and you get final bounding boxes. This technique is also called Nomex suppression. So after neural network has detected all the objects, you apply Nomex suppression and you get these unique bounding boxes. There could be another issue is, what if a single cell contains the center of two objects? In this case, the dog and the person both are in the middle grid cell. Now we use this vector to represent the grid cell, but see, this vector can represent only one class. So how do you represent two class? Well, I have this value for dog, I have this value for person. So instead of having a 7-dimension vector, how about we have a vector of size 14, where you're just concatenating these two vectors. Okay, so this is said to have a, basically it has two anchor boxes. So this is one anchor box, this is second anchor box. So here you have two anchor boxes, and you can actually have more than two anchor boxes. Let's say if there are three objects which has the same center, then you can have three anchor boxes, you can have five anchor boxes. But if your grid cells are small enough, then in real life it's hard to have many objects belonging to one grid cell. So now CNN with two anchor boxes will look something like this. So instead of a vector of size, the only change is now you have a vector of size 14. If you want to have three anchor boxes, you will have a vector of size 21, 7 into 3. Okay, and that will give you your final output. So that was all about you only look once, or YOLO algorithm. It's a very, very fast algorithm. Even on a video clip, which is, let's say, at 40 frame per second, it can detect objects really fast, and it is the most modern way of detecting objects. So if you're in computer vision fields, if you want to do object detection, you have to use YOLO because it is very fast and accurate. In the next video, we will be looking at some code. We'll do real object detection in image and in video using YOLO framework. I hope you're liking this series so far. If you do, give it a thumbs up and share it with your friends. Thank